Alright, so in this video, I'm going to be talking about Kullback-Leibler divergence, or KL divergence. So you might ask yourself, what is that? Like, what is it? What does that complex, jumble of words even mean? Well, I'll show you what it means in this video. Alright, so what we have here is bits of information, or ones and zeros. So three examples of that would be 1010, 0111, or 1001. Those are bits of information. And you can represent different things with different combinations of zeros and ones, or actually permutations, sorry. Permutations of zeros and ones. Combinations would just be like, two zeros anywhere, but we're using like permutations to represent different things. So in order to calculate the number of permutations, we say that if n is the number of placeholders, or the number of those orange lines, then 2 to the n is the number of unique representations of things that we can encode. So in the first slot, it could either be a 1 or a 0, second slot 1 or 0, third slot 1 or 0, and so on. So note that it doesn't have to be ones and zeros. It could be like, I don't know, the green and blue, or phone and laptop, or true or false. It could be anything that's like binary, So you could represent different things with different permutations of those things in placeholders. So let's generalize this a bit more. So say that we still have n is the number of placeholders. We're going to have b is the number of encodings. So in each placeholder, we're going to have a 0, 1, 2, 3 for 4 in each placeholder. Or we could have like 0, 1, 2, 3, 4, 5 for 6 in each placeholder. And the way that we'll calculate the number of permutations, or the number of things that we can represent with that code, with that encoding, is b to the n, where b is the number of things, the number of items within each placeholder. And so b to the n is the number of unique representation of things that we can encode, which is pretty cool. Thus, if we have n, which represents the number of bits, so, n represents the number of bits. So that's the number of placeholders. And when you have 2 items per placeholder, the placeholders are called bits. But then when you have more than 2 items, or however many items per placeholder, they're called bits with quotes. So if we want to represent a certain number of permutations, like a certain number of things, which is equal to x, which is b to the n things, then that would be n is log base b of x bits. So it takes n bits, or log base b of x bits, to encode that much information. All right, but how much information does it take to encode a probability? Like, how much information does it take to encode, I don't know, 1 out of 64, or 0.35 as a probability? So to answer this question, note that we could always represent p, the probability, as 1 over p. So that's important because you're going to see that 1 over p, which is the denominator, is going to be important for calculating how many things we have to encode in order to represent this probability, which leads to how many bits we need to have to represent this probability. All right, so when you say p is 1 over p, this means that one outcome of 1 over p possible outcomes is represented as the thing that happens. So basically, you have a picture, right? In this picture over here, you have 10 circles total, and one of them is red. And that's a representation of probability. You could use this picture of one red circle out of however many circles, 1 over p circles, where P is the probability, to represent a general probability in general. You can always represent it in that way. So that means that negative log base B of 10, that would be the number of bits that you need to encode this probability. And you only need the denominator because you could create the picture with the 1 over P when you have it in that form right there, 1 over P, which is pretty cool. And it took me a while to think about this, but I kind of came up with this idea of representing it like this, and it's like, oh wait, that makes sense because that's how much information you need to represent that picture. And the picture represents a probability, and a unique probability too. So what I was saying was that each probability can be mapped to a unique diagram. So there's a one-to-one mapping between probability and diagram. And the probability is specified, or sorry, the amount of information you need would be specified by the denominator when it's in P is equal to 1 over P form. So that's what I was saying on the last slide. And thus the number of bits required to represent an entire probability distribution would be the number of bits that you need to represent each probability summed together in that distribution. So that would actually be negative log base B of P of x, because P of x is always less than 1, and when you take the log of something that is less than 1, you're going to get a negative. But we want to represent our information as positive numbers, so that's why we have the negative in front of that log right there. And we also have the entropy of a distribution, and that is the expected value of how much information you need to encode a probability at a given x. So it's going to be the sum over all x of negative log base B of P of x times P of x. And that's just the expected number of bits for some x. And so there's also something called a cross-entropy. And what this is that say that you have a distribution P of x, and instead of using log base B of P of x, or sorry, negative log base B of P of x to represent the amount of information needed to encode some probability P of x at x, and instead you use Q of x, the amount of bits needed to represent the probability Q of x at some x, at the same x, I mean, then you're actually going to end up using, on average, more information to represent the P of x, so more information than you really need. So you're going to be using excess information, really. And, oh, sorry, that was Siri. No, Siri, I'm not talking to you. All right. So what this is going to be is it's going to be the sum over x of negative P of x log base B of Q of x. And you'll see why cross-entropy and entropy are very important soon. So as I was saying, cross-entropy is basically the idea that if we say that the number of bits associated with each x is the number of bits according to Q of x at some x instead of P of x, then that's cross-entropy, really. And we're going to end up having an excess amount of information on average. And you'll see why we do this. So say that we have two probability distributions, P of x and Q of x. So how do we measure how different they are? Well, one intuitive way to do this is to use Euclidean distance. So what I mean by this is that for each x, we're going to take the difference between the probabilities P of x and Q of x, and we're going to make sure that they're positive by squaring them. And it doesn't matter if we square them because it's still a monotonic increase. So we're going to sum those differences so that the greater the distance, or sorry, the greater the difference is, the total difference, the greater the Euclidean distance, and therefore the greater the difference between the probability distributions. However, we're we're only measuring the absolute difference, but what if we want the relative difference between them? Well, we'll need a different set of tools, mathematical tools. So let's now think in terms of information. We want to measure how different distributions p of x and q of x are from one another in terms of their information content. So your first instinct may be to take the difference between the total information content present in p of x and q of x, or maybe to take the difference in expected information content between p of x and q of x. However, these two methods are not as good mathematically for some reason. I really don't know why, actually. That's what I would have thought to do, but for some reason the KL divergence is actually better than these two methods. And I think it's because of the mathematical properties, which I haven't really delved into much, but you'll see KL divergence next. So conceptually, what KL divergence is the difference between cross-entropy and entropy. So this is actually going to be the extra information that it takes to describe p of x using q of x. So yeah, pretty interesting. And you may have noticed in the previous slide that I used the term extra information. And the reason why I use that is because we're going to actually see that cross entropy is going to always be greater than or equal to entropy. So it's going to be greater than entropy when q of x is not equal to p of x. And it's going to be equal to entropy when p of x is equal to q of x. So you can see that from the mathematical properties of the simplified form of this cross entropy minus entropy formula for KL divergence. So we're going to proceed with the simplification by using the distributive property first. And then if you use the property of logs, where subtracting them is equivalent to dividing them in the parentheses, then you get your final formula for Kullback-Leibler divergence, which is dKL p double bar q is equal to that summation right there, where the sum over x of p of x times log base b of p of x over q of x, where b is the number of items per placeholder, or that's what kind of bits you're using. And so another thing I want to mention is that if you were to take dKL q double bar p, so you're going to rearrange it so that p is in place of q and q is in place of p, then it's actually not equal. So that's why it's called a divergence and not a distance, because they're not equal. And KL divergence, you're taking the expected value of the differences in probability, or the relative difference in probability in terms of information. And you could also express it in integral form if you have a probability density function, or two probability density functions, p and q, lowercase q and lowercase p. All right, that is the end of this video, and thank you for watching.